Hey, welcome back to Math with Patrick and Quill. It's March 11th, and we're doing problem 70 together today. So y is equal to the cosine of pi over 5 minus cosine of 2 pi over 5. And once we find this value for y, once we raise it to some exponents and then add these all together, we should get 11, which is today's date. So I can already kind of tell that this number right here needs to be 10 because, well, plus 1 is 11. I'm not really looking forward to this part because with trig functions like sine or cosine or tangent, some easy angles are going to be like pi over 2, pi over 3, pi over 4, and pi over 6. And kind of notably, pi over 5 is missing right here. This one is a lot harder to get, but we're going to do it anyway. And I also noticed that there's this 2 pi over 5, and there's a few different ways we could like go around or to get this value. There are such things called these like sum formulas for cosine and sine. So I could think about this as cosine of pi over 5 plus pi over 5, and then maybe solve it that way. But I'm going to do something a little bit different. And here, I'll show you what I mean. If we do y equals, and then it says cosine of pi over 5, I'm just going to say theta for now. Theta is just a Greek letter that you can use for angle measurements. And so 2 times pi over 5 is going to be 2 theta. And I'm going to use a double angle identity for cosine here. So double angle identities can come in handy when you have 2 times an angle on the inside here. And usually these are things that you just kind of like look up and figure out. I'm sure there's proofs, but I actually haven't done one in a while. So cosine of 2 theta is going to be the same as 2 times cosine theta. And then so I'm going to square this guy. So cosine theta times cosine of theta. And for notation, you can put a squared there. It's a little strange, but that's just kind of convention. And then minus 1 to complete this double angle identity. So I replace this double angle, and now I have a single angle. And my goal here is I only need to worry about this cosine of pi over 5 instead of this 2 pi over 5. And then just kind of rearranging some terms, y is going to be equal to negative 2 cosine squared theta plus cosine of theta plus 1, because I'm kind of distributing that negative. And well, this theta all along has been pi over 5. So now the question is, what is cosine of pi over 5? Because once I get that, I can plug that in here and solve for y. In a previous video, January 20th, I came across something called the golden triangle. This is an isosceles triangle with a 36-degree angle measurement here. And it's isosceles, and so these are the ones that are equal to each other, and these are both 72 degrees. You could check, these all add up to 180. And the reason why I'm choosing to bring this triangle up is because pi over 5, the angle in radians, is equal to 36 degrees. With radians, you kind of work with like, you start by thinking that the circumference of the unit circle, so radius of 1, the circumference is going to be 2 pi. And so as you trace along the distance of your circumference, you're kind of also tracing an angle out on the inside here. So 1 pi radians will be halfway. And so here you can kind of see that pi radians is the same as 180 degrees. And then if you divide both sides by 5, that's how you can get that 36 degrees. And I still want to figure out what cosine of pi over 5 is. And I'm going to use something called the law of cosines. It's an equation that you can use whenever you're doing stuff with triangles. And it doesn't have to be a right triangle, actually. It could be pretty much any triangle. C squared equals a squared plus b squared. Here it is the Pythagorean theorem right now, but then the law of cosines adds this, or I guess subtracts this extra term right here. Interestingly, if the angle C, so big C is going to correspond with this angle measurement, 36. If that were a 90 degrees, cosine of 90 is just 0. And so in the case where you use the law of cosines on a right triangle, you just get back to the Pythagorean theorem. This formula helps you learn stuff about side lengths of triangles and also angles too, because of this cosine part. And then in the video from January 20th, I figured out that the side lengths of this golden triangle are going to be 1 and 1. Again, it's isosceles, so those are the same. And then this one is, let's see, root 5 minus 1 over 2. And that number was pretty hard to get, but I found it with some clever geometry and algebra at the same time. Ultimately, I want to know cosine of pi over 5, or cosine of 36 degrees. That's the same thing. So plugging in the numbers, this C represents the length opposite the angle C. So I'll go C squared equals A squared plus B squared minus, and then 2AB, since A and B are both 1, I'll just do a 2. So 2 times 1 times 1. And then cosine of C. And angle C right here is the 36 degrees. I'm just going to call it pi over 5 because that matches today's problem. And so if I just reorganize all of that equation to isolate cosine of pi over 5, now I know the value of cosine of pi over 5. So let's see. The right side seems easier to simplify because this is just 2 minus 2 cosine of pi over 5. The right side is a touch harder. Let's see. When you square fractions, you can square the top and bottom. This turns into a 4. Foiling the top, I get, so root 5 times root 5 is 5. And then I have minus 2 times root 5. That's going to be my middle terms, and then plus a 1. I guess I'll just keep that step right there for now. I can combine the 5 and the 1 to be a 6. So I have a 6 minus 2 root 5 over 4. That can simplify. I could take out a 2 from all of those. So here I am reducing the top by a factor of 2 and the bottom by a factor of 2, thus not changing my fraction. And let's see, I'll just rewrite the left side the same way. To isolate this cosine of pi over 5, how about I will subtract the 2 and then divide by negative 2. So subtracting by 2, I want to make sure that I basically have one fraction on the right side. And so I think I'll actually go minus 1 minus root 5 over 2. Essentially, I just subtracted this 3 by 4, but then ultimately having this divide by 2 on the bottom, this is the same as just subtracting a 2. And then dividing both sides by this negative 2 now, dividing by 2 would look like maybe multiplying the denominator by 4. And then the negative will negate one side, either the top or bottom. And so this is my value for cosine of pi over 5. Cool. Let's bring that back up to here. So y is going to be equal to negative 2 times this value squared. So 1 plus root 5 over 4 squared. Then I'll do plus, the value itself, 1 plus root 5 over 4, and then finally a plus 1. I don't see a better strategy than just expanding and then simplifying, so I'll do that. Y is equal to negative 2 times, and then I'll expand the top part. So same thing as before when you're squaring a fraction. Let's see, that happened right over here. You square the top and square the bottom. So this is a 16 now. And then the top, I have a 1 plus a 2 root 5 plus a 5. Then how about, I'll merge that negative 2 in a bit. I'll just rewrite everything else as normal. Don't want to do too much all at once. Let's see. So simplifying this part, I get a 6 plus 2 root 5 on top. And then this 2 and the 16 can cause an 8 on the bottom. and I still need this to be negative because of that negative sign. Now it looks like, I could simplify this a little bit further. That's a 3, and then I can get a 4 on the bottom, and then that 2 can go away in front of the 5. All right. And then I'm going to add that to 1 plus root 5 over 4, and then finally plus 1. These have a common denominator, so I can shove the numerators together. That's going to be 1 plus root 5 minus 3 minus root 5 all over 4. Finally, the plus 1. Y is equal to negative 2 over 4. Here I notice that the plus root 5 and the minus root 5 cancel out. Ultimately, y is equal to just the number 1/2. Pretty simple. All of this stuff here, we get a very easy fraction. Y is equal to 1/2. So that means x is now equal to 1/2 to the negative 3 plus 1/2 to the negative 1 plus 1. Now, working with these fractions and these negative exponents, I like to just get rid of negative exponents as soon as I can. And one way to get rid of them is if you flip the fraction and take away the negative sign, that leaves the value the same. So I could flip the 1/2, make it a 2, and that can remove the negative sign for me. Same thing's happening here. I can flip this, remove the negative sign, and this plus 1 is still just a plus 1. And then finally, it looks like x is equal to 8. Oops, I missed this plus sign. 8 plus 2 plus 1, and that is 11. Wonderful. That's today's date. X is 11. What a problem. Using some geometry, using a lot of stuff with like algebra and like square roots, and then finally some fractions and negative exponents, all to get the number 11, which is today's date. So we are all done today, and I'll catch you in the next video tomorrow. All right, see ya.